are going to discuss about the topological sorting. So this is another interesting problem which we are studying under the decrease and conquer technique. So in the previous sessions we have seen the depth first search and the breadth first search. Now before going into the what do you actually mean by topological sorting or topological ordering, let's try to understand by considering a simple example. Say for example you want to solve one particular problem. Now if you want to solve a problem, or let us say that you want to execute one project, now what we generally do is, now we can divide that project into several smaller parts or subtasks and assign that to few teams, right? Now what is our actually intention is to estimate the time required for the completion of all these small tasks, so that now you can finally get the complete project done. So if you try to draw a graph now, right, so when you are going to assign these subtasks to individual team, you know that these team can execute the project parallelly, or sometimes it may happen that one team cannot start the project until it gets input from some other team. So that means now we are having some preconditions and certain constraints for carrying out our subproblem. Now if we try to consider these subtasks as a vertex, now you can try to draw a graph. Say for example, now A is one small problem or one particular subtask you want to do, and B is another task you want to do it. So we'll write it as B. So now you have another task C. So now once you finish A, so you go and finish this task B. So then you go and finish this task C, right? So like this, if you are able to draw a graph, a directed graph, right? So now where this direction indicates the order in which they must be executed. Now this direction indicates the order in which you want to execute your particular project and try to complete. Now when you are trying to draw such a type of a directed graph or a diagram, now you have to remember that, so now this graph should not have any cycles, because if you get a cycle, now this becomes a case of a deadlock and you cannot solve the problem. So we have to see that, so you should have a directed acyclic graph, or it's also called as DAG, D-A-G. That means directed acyclic graph. Now if you have got a directed acyclic graph, so then you can try to solve this particular problem, or we say that we can find the topological ordering, right? Now what does that mean now? Now when you are going to create a directed acyclic graph, now our intention is to find the sequence, right? You want to know in which sequence, whether after A, B is executed, or after B, task C is executed. What is that sequence? So we have to find a sequence of subtasks, the order in which these sequences have been completed, that means jobs have been executing. So to find such a sequence, we call it as a topological ordering, a topological sorting, right? Now this is how, now mathematically if you are going to define a topological sorting, now this is how we can try to define. Now if you have a directed graph G, now if you take a particular directed graph G, then the topological sorting or ordering of a graph is a linear order of vertices. So it is a sequence of vertices in certain order, right? Such that if UV is an edge in the graph, so in this graph you take any edge, any directed edge, like say for example if you take this edge, right, when you take this particular edge, so this edge comes with two vertices, right? So let us assume this is vertex U and this is vertex V. So if you consider an edge UV, so is an edge in the graph, so then U should come before V in the topological order. Now if you look into this graph now, U is from U only you are going to V, that means U is before V. Now if you find the topological ordering, that is try to find the topological ordering, in that ordering also you should come before V. So such a type of ordering, now we call it as topological ordering, right? So now in order to find the topological ordering, now we have two ways. So we have two algorithms or two methods we are having. The first method is by using the DFS, that is depth first search. Now in our previous videos, we have already seen what is a depth first search traversal. Now how we are going to use it. So now how do we apply the DFS algorithm to this particular directed acyclic graph and find the topological order? So first step, what you are supposed to do is, now you are supposed to perform DFS travel. So apply your DFS algorithm for your given directed acyclic graph and note down the order in which the elements becomes dead end, right? So you should know the order in which elements become dead ends. You know that in DFS algorithm, whenever we get a dead end, we pop the vertices from our stack, right? So we are going to pop it from the stack. So the order in which we are going to pop it from the stack is written as second subscript. If you remember that, so in DFS algorithm, now when you are going to write each vertices, now you are going to use two subscripts below this. Say for example I and j. So we were taking two subscript, right? So the first subscript tells us the order in which this vertex enters into our stack. The second subscript tells us the order in which this particular vertex is popped from our stack. So we are maintaining two subscript. So in finding topological ordering, now our second subscript is important for us, because this tells us when we have reached the dead end or the order in which the vertices are being popped from our stack. So once you collect all this ordering, once you write all this ordering, now you are supposed to reverse this order. So if you reverse this order, so you will get the solution to our particular problem, or you can say the topological ordering, right? So now let us try to consider this example. Now we have got an example. Let me just wipe it off, right? So now consider this particular graph. Now before you try to solve it by using DFS algorithm, that means finding the topological ordering of this, now you have to see that now this graph is a directed acyclic graph. Now when you look into this graph, now it is very clear that it is a directed graph, because there is a directions are been given. Now you check that whether it is acyclic. That means there should not be any cycle. No any cycle means, say if you consider any vertex A, now is it possible for us, does there exist a path in this graph such that from A you can go to some vertices and come back to A? Now let us see. So from A you can go to B, from here to D, right? From here you can go to F, but you cannot come back. You cannot come back to A. You take any vertex, say you take C. From C you can go to D, you can come to F, but you cannot come back to C. That means there is no cycle. So clearly this is a directed acyclic graph. So we can solve this particular problem. We can find the topological ordering of this particular problem. So now how do we do in the first method? By using the depth first search. Now what does the DFS says? Already you have solved few examples, right? We start from any arbitrary vertex A. Let us say that you start from this vertex. This is your starting vertex. So we push A into our stack. So we push this vertex A into our stack. Now as soon as you push A into this stack, we mark this A as visited. So now vertex A is visited. So in the first subscript we will write A1 comma. That means A is the first vertex which enters into our stack, and we mark A as visited. Now from here we check adjacent nodes. So from A we can go to B, or you can go to C. So we have two nodes. So chronologically we will select, let us assume now we go to vertex B. So we push B into our stack, right? Which is the second vertex which enters into our stack, B. So below B we write 2. So 2 indicates that B is the second vertex which is entering into our stack, right? So now B is visited. Now from B you have only one direction, you can go to D. So push D into our stack, right? Now D is the third element which is going into our stack, so we will mark it as 3 in the first subscript. So we will say now D has visited. From D, where you can go only to F. There is only one edge, so go to F. Now push F into our stack. Now we say that F is visited, right? So now F is the fourth node which is visited. So we will write 4 comma, right? So now we are at F. So F is visited. Now from F in to which node you can go? You cannot go to any node from F, right? So now F becomes a dead end. When F becomes a dead end, we are going to remove this F from our stack. We pop this F from the stack. So when you remove this particular F from the stack, so we write the second subscript. Now we will write second subscript for F. We update it as 1. So which indicates that F was the first node which you are going to pop from your stack, right? So now F is removed from the stack. Now the top element in the stack is D. So we will come back to D. Now from D, any other adjacent node which you have not visited, but from D you can go only to F, but F is already visited. So now D becomes dead end. So there is no way. So now what we do, we remove D from the stack. We pop D from our stack. So below this D vertex D, this subscript what you are going to mark, you are going to mark it as 2. Why? Because D was the second vertex which you have popped from our stack, right? So next element, topmost element is B. So we'll come to B. Now from B you can go only to D, but D is already visited. So now B becomes the dead end. So what we have to do, same process, pop B from the stack. Now mark B is the third vertex which has been removed from your stack. So 2 comma 3. So B will, here we are going to write 3. So now the top element in the stack is A. So we'll come back to A. Now from A you can go to B or C. Now B already visited, so you need not go. But C is not visited. So from A now we will go to C. So that means you insert C into your stack. Now you are going to insert C into our stack. Now C is the fifth element which now we are going to enter into our stack. So C is the fifth element which we are entering into our stack or pushing it into our stack. So now we mark C as visited. So from C now we check which are the adjacent nodes we are having. So here now we can go either to D or node E, but you have to see that D is already visited, right? D is marked as visited. So now you are going to see that you have a node only E. So E is not visited, right? So now what we do, we push E into our stack. So in our stack we push E. So now E is the sixth node which enters into our stacks. We will write 6 comma, right? Now you will mark C as visited. Now from C only to F, but F is already visited, so now you cannot go, so that means E becomes dead end now. So now we will pop E outside. We will pop E from our stack. Now see, E is the which element which is coming out. See, F was the first element, D was the second element which we popped, D was the third element. Now E is the fourth element which is popped from our stack. So this becomes E becomes now 6 comma 4. So you have removed this. Now the top element in stack is C. We will come to C. From C either D or E, both are visited now. So now C becomes the dead end. We pop C from our stack. So C is the fifth element which you are going to pop from your stack. So here we will mark it as 5. So now check, any element is left in our stack. Yes, A is left, right? We will come to A. So now A, from A, B and C. B is also visited, C is also visited. A becomes the dead end. So we will pop A outside our stack and we will say that this is the sixth element which is going to pop from our stack. So now check the elements in our stack. Now the stack is empty. You don't have any elements in our stack. And also look all the vertices of your given graph. Now all vertices are marked as visited. So you don't have any vertices which is marked as unvisited. So you can stop your algorithm. So once you have applied now depth first search on this graph, now this is the traversal what we got, right? So we will see here. Now this is what the traversal what we have obtained here, right? This is the traversal what we have got. So there are two subscripts. In DFS, when you are traversing, you write for each vertex. The first subscript indicates the order in which it enters the stack. Second subscript, the order in which you are popping the stack. Now once you have got the traversal, now what you look into the second subscript, and next step write the order of elements which are being popped from your stack, right? You now observe only the second subscript. Which is the first element which is going to pop here? This is the sixth. A is the sixth element, B is the third element, D is second, F is the first element which you are going to remove. So write F first, right? F is the first element. Now which is the second element you are going to pop? D, because D is the 2 is there, right? D is the second element, write a D. Similarly, B is the third element, E is our fourth element, C is the fifth element, and A is the last element which you are removing from the stack, right? So now you have written the sequence in which the elements are popped. So once you got this particular sequence or order, reverse this. See here, which is the last element? A. Now A becomes the first element. You reverse it. So A, next will be C, next will be E, next will be B, D and F. So now when you reverse this, now this is the topological ordering. This is your final answer. So this is your topological ordering of your given directed graph. So this is how we are going to solve this particular problem. So in the examination, now when they give you to solve a given directed graph, first thing is that you first check the graph is a directed acyclic graph, right? Then you see which method they are going to ask. If they have asked using the DFS method, DFS traversal, now you have to explain it in properly, step wise you have to explain. Simply if you just write one line and write these 3 lines, you cannot get to complete marks. So every step, so in the first step what we are doing, so how we are pushing that element into the stack, then second element, third element, you have to explain it in your own terms so that you will get complete marks, right? Now this is a very simple example we have seen. Now let us take another example and we'll see how we are going to find the topological ordering. So now you have got a graph here. So this is a directed acyclic graph. So you are going to apply the DFS algorithm. So now you have a stack here, right? Now you start from any vertex, right? Let us see, you can start from A or you can start from B. If you consider B as your starting vertex, then the sequence will be different, right? So hence there can be more than one topological ordering for a given graph. That is not a rule that you should have only one. So let us try to solve, apply the DFS. So first we will start with the node A. So now A is the starting node which we are going to start, right? Okay, so we will write it with capital letters. So now A is the starting node. So which is the first node which enters into our stack? A is the first node which enters into the stack. So we will write A, comma. So from A you can go to C only. So you push C into your stack. So C is the second node which you are entering into your stack. So we will write C2, comma, right? So this is 2. So from C you can go to D. You push D into your stack. So D is the third element which you are pushing into your stack. So you write D3, comma. From D you go to E, right? You push E into your stack. Now E is the fourth element which you are pushing into your stack. Now from E you cannot go in any way. that means you have reached a dead end. Once you have reached the dead end, so what you do, you remove E from your stack, you delete E from the stack, and you say that E is the first element which you are removing. So 4 comma 1, so E was the first element which was popped. So you can see here popped element, so E is the first element, so I will write E here, right? So now we will come to our stack. The topmost element is D, so that means we go back to D. Now from D, adjacent nodes, from D you can go only to E, but E is already visited, so now D becomes dead end. You pop D from your stack, so D is the second element, so this becomes 3 comma 2. So D is the second element which you are going to pop, so we will write D here, that is the popped element, right? So we will come back to our stack. The topmost element now is C, we come to C again. Now from C you can go to D or you can go to E. Now C to D, D is already visited. Now whereas E, you see, now E is also, have you visited E? Now E is also visited. So now C becomes the dead end. So you are going to remove C, right? So C is the third element. So this becomes 2 comma 3. So C is the third element which you are going to pop out. So we will write C is the third element which has been popped out. So now the left element is A. So we will come back to A, right? Now from A you can go only to C, and C is already visited. So now A becomes dead end. You remove A from your stack. So now A is the fourth element which you are going to pop from your stack, right? A is the fourth element. Now you check your stack. Now stack is empty, right? Stack is empty. Now see your all the vertices of your node. Now you know that A is visited, right? Now C is visited, D is visited, and E is visited. Now whereas B you have not visited. Since you got one node which is not visited yet, again apply the DFS algorithm. Again apply the depth first search algorithm. You start from B. So you push B into your stack. Now you will push B into your stack. So now B will be the fifth element which enters into your stack. B is the fifth element which it enters into the stack, right? So you mark B as visited. Now from B you can go to C, but C is already visited, right? C is already visited. You don't have the direction or there is no other node. So now D becomes dead end. Once D becomes dead end, you pop D from your stack. You remove D from your stack. So D was the sixth element which you popped. B was the sixth element which you popped from your stack. So we will write B. So now all elements are marked as visited and stack is empty. So you can stop our depth first search algorithm, and this is the order in which the element was popped, right? The first element which you have popped was E, the second element was D, the third element was C, and the fourth element was A, and last element was B. So we have written the order. So now to get the final topological answer result, what we do, we reverse this. So this you are going to reverse, right? So B is the last element. Now you try to reverse this. So you make B as your first element, then A, C, D and E. So this is the final result, that is topological ordering by using depth first search algorithm. Clear? This was the first method of finding the topological ordering or topological sorting by using DFS algorithm. So in the next session, so we will take the second method, which is called as source removal technique. Okay, we will look into the source removal technique. Hello, welcome back to the next topic, that is the source removal technique. So in the previous session, now we have seen how we are using the DFS algorithm and finding the topological ordering. So in today's session, so we will be looking into our second method. So the second method is called as source removal technique. Now basically the source removal technique, now we are trying to apply the decrease by 1. that is in our decrease and conquer. So this is decreased by 1. We try to reduce the problem by size 1 in every step. Okay, so now to apply this source removal technique, the key idea here is that now we are supposed to find the in degree. Right, now we are supposed to find something called as, or we try to define a term called as in degree. So what is the in degree? So let us try to understand. So let us take that same example of our graph. Now we should know what is the definition of in degree of the individual vertices. So now when you look into this, these are the directed graph, right? So in any directed graph, now we know that all edges are either coming to one vertex or leaving from each vertex, right? So you know you should look into what is the definition of in degree. Now if you take individual vertices, now edges either goes towards that or leaves from that. So now when you are talking about in degree means the total number of edges which are coming towards that particular vertex is called as in degree. The total number of edges going out from a particular vertex is called as out degree. So for our source removal technique, that is for our second method of finding topological ordering, now we are interested in the definition of in degree. So now the first step what we have to do is that you are supposed to calculate the in degree of all the vertices. Let us say that this is our given graph. Now you have to find the in degree of each and every nodes or vertex in our graph. Now let us start with the first vertex A here. What is the in degree of A? How many edges are coming towards A? Now you can clearly observe that there are no edges which are coming towards A. So the in degree of this node is 0. We will calculate the in degree of every node. So in degree of A is 0. Now come to node B, or vertex B. Now what is in degree of B? Now you can see that there is one edge which is coming from A to B. Right? There is only one edge. So in degree of B is calculated as 1. So in degree of B is 1. What about C? Now C in degree also 1. D. Now for D, there is one edge coming from B. There is another edge coming from C. So in degree is total number of edges. So in degree of D is equal to 2. Right? In degree of D is equal to 2. Now in degree of E, so you can say it is 3, and in degree of F is also 2. Right? Now the first step what you are going to do is find the in degree of all the nodes. Now once you form the in degree, calculated the in degree, in the second step you identify the vertex whose in degree is 0 and delete that vertex. So now you have to identify the vertex whose in degree is 0 and delete that particular vertex. Now if you look here, now vertex A's in degree is 0. Right, vertex A's in degree is 0. Now what you have to do in the next step, you are supposed to delete this vertex. Now when you delete this vertex, now this edge also will be deleted, this edge also will be deleted. Now you draw a new subgraph. Right, now because this vertex A's in degree is 0, you delete, you simply just delete it and try to draw once again the diagram. Now when you delete that particular vertex A, and when you try to draw a new subgraph in the next step, right? So now this is the graph what you are going to get. So what we have done, we have deleted A. So we have deleted vertex A whose in degree was 0. When you delete A, the two edges also will go off. Now you will get new subgraph. Now apply the same method. Calculate the in degree. Now what is the in degree of B? So in degree of B is 0, right? Now in degree of C is 0. In degree of D is 2 because there are two edges coming to D, and in degree of vertex E is 1, and in degree of vertex F is 2. Now identify the vertex whose in degree is 0. Now in this case we got two vertices whose in degree is 0. Now which one to delete? Now you can delete any one. right? In each step you have to delete one node whose in degree is 0. Now arbitrarily let us take node B and we will delete B, right? You can delete either B or C, but let us assume we will go with chronological ordering. We will delete node B. Now when you delete this particular node, this edge also will go off. Now you draw a new graph. Now what will be your new graph? So it will be this one. So D, C, E, F. Now it is constructed here, right? When you delete that node B, now you get a new subgraph. So this subgraph looks like this. Again calculate the in degree. So now in degree of C is here 0, this in degree of D is 1, E is 1 and F is 2, right? So now C has got in degree 0. Now what you have to do in the next step? So you have to delete C. So delete C. When you delete C, now you get another subgraph. Now this is the subgraph which you are going to get in the next step. So every step now you are supposed to, in the examination you are supposed to draw small subgraph, and you have to explain that you are calculating the in degree, right? So and mark the in degree on top of this vertex and try to say that, write in your English sentences that what step process you are trying to do. So now once you delete C, once the node C is deleted, the new subgraph you are going to get this. Now same method you are going to continue. Now in degree of D is 0, calculate the in degree, E is also 0, F is 2, right? Now again you got two nodes with in degree 0, so we will delete any one first. So now let us say we delete node D. When you delete the node D, if you delete this node D, this edge also will go off. We will get a new subgraph which has got only E to F. So this is the next step graph what you are going to get, right? Now in degree of E is 0, F is 1. So you are going to delete E. Now when you delete E, you will get only one node F, right? In the next step, what is in degree of this F? It is 0. So you are going to delete F also. So now you have an empty graph. So now what we have done in this particular process is, every step we are calculating the in degree and you keep on deleting the vertices. Now the order in which you are deleting the vertices or nodes, you have to note down that order. So the first node which you have deleted from our graph was A. First you deleted A. So you note down the order in which these nodes are been deleted. First you deleted A from your graph, then you deleted B. Next here you deleted C. You got this subgraph. In this you deleted D first, right? So then you got this subgraph. Then you deleted E. And last you got F, one node, and you have deleted that node also. So the sequence in which you are deleting this particular node is your topological ordering. So is your final result. Now this is the topological ordering of your given directed graph, right? So this is your topological ordering. Now this is how now we are trying to use the source removal technique in order to find the topological ordering. So now let us take another example. So with this graph we'll try to see, right? Now this was the graph. This is the graph what we are having. So now you are going to start first step. What is the first step? Find the in degrees. Now in degree of A is what? 0. We calculate the in degree of B. It's also 0. What about C? 2. There are two edges coming to C, so this becomes 2. D, it is 1, and E is 2. So now you have two nodes whose in degree is 0. Delete any one. So first step we will delete A. So when you delete A, you get this subgraph. So what is the node you have deleted? You have deleted A. Now again calculate the in degree. In degree of B is 0 here. Now C is only one node. You are coming towards C. So this is 1. D is also 1 and E is 2. Now you have got B whose in degree is 0. So in the next step we will delete B. Right? You delete B. So you get this as a subgraph. Now for this subgraph again calculate in degree. For C it is 0, D 1 and E 2. So in the next step you are going to delete C. So you delete C. So when you delete C you get these two nodes. This is a new subgraph. Now again calculate in degree. This is 0 and 1. Right? Now in the next step you are going to delete D. So when you delete that D, so you will have only one node E. So what is in degree of this? It is also 0. So you delete this. This is the last node which you have deleted. Now you don't have any tree. So now the order in which it is deleted was A, B, C, D and E. So this is the topological ordering of this given directed acyclic graph. Right? So this is what now about the topological sequence or topological ordering of the vertices. Right? So now you try to work more examples, try to take the examples, and when you work more examples you will come to know. So in our lab session, so we are going to implement the second algorithm, right? Topological sorting using source removal technique. So when we are discussing the lab session, now at that time we will try to discuss the algorithm, right? We'll try to discuss the algorithm for both the DFS, that is how we are going to use the depth first search in order to find, and the algorithm for source removal technique. So how we are going to implement this this particular, how to find the in degrees, right? So how we are going to calculate the in degree of all the vertices and remove the vertex whose in degree is 0. So we will try to look into that algorithms in our lab session. So but right now we have seen in today's one of the very interesting topic, that is topological sorting or topological ordering of our vertices. So we have discussed two techniques here. The first one was by using our depth first search algorithm, and the second technique is by using source removal technique. Okay, I hope you are very clear with this particular problem and how we are going to solve this problem. Now still if you have any doubts, you can just drop the queries in our classroom. Thank you for watching.